Okay, let's continue the topic of differential amplifiers. This is where I stopped in my last recording on a BJT pair in the common mode operation. So let me take one more minute, finish up BJT, and then we'll look at some problems on all of this. So moving on to the next slide, it shows the BJT now operating in differential mode. And there are three examples given in our textbook of differential mode. In one case, a 1 volt is applied only on one transistor and the other is grounded on the input of one transistor, the base. In the second case, we have a minus 1 volt applied and the other is grounded. Lastly, we have a small voltage, not specified, but we assume this is a signal voltage, Vi, that's applied. So this you can consider large signal because 1 volt is pretty large compared to definitely overdrive voltages. So basically, to understand what is going on here, the notes here may help. So when you have differential inputs to a BJT pair, one device will be on and conducting all of the current I, and the other device will be off because the other device's base is grounded, right? So for a device to be on with its VB equals 0.7 volts, its emitter has to be approximately 0.3 volts, right? So if this has to be on, its emitter is at 0.3 volts, right? We know that that is the condition for active operation. So once you apply 0.3 volts here, the other immediately goes into reverse cutoff because this junction, the base to emitter junction, and remember the base is already grounded, so the base to emitter junction has become negatively reverse biased, not negative but reverse bias. So that's what happens. Similarly here, if you apply a minus 1 volt on Q1, that becomes off, negatively biased, or sorry, reverse biased. And the other device, Q2, even though it is at ground, because this is much more negative, right, minus 1. So Q2 is on and Q1 is off in this case, okay? So make sure you understand the logic here. And also the other factor to remember is that the current is in the on device only, which is alpha I in the collector and I in the emitter. In the other transistor, it's entirely zero. And so the output voltage here will be, because this is zero current, it will be the VCC coming here. But here the output voltage will be this VCC minus the drop across RC. Okay. Lastly here, where we talk about the amplification behavior of a small signal condition applied at the input. We talked about this delta I, right, when we were discussing MOS behavior. The same thing is true here. This delta I, which is the change in current compared to common mode operation, that delta I is proportional to the input Vi, a small value, and the output voltage then is 2 alpha delta I RC. In case of the MOS, we didn't have the alpha factor, but here the alpha factor comes in because these are BJTs. But this analysis, if I have the time, we'll do small signal analysis in some more detail on BJTs also. But otherwise, the analysis will look like what we'll do for the MOS. But I hope with this little introduction to BJT, you at least learn that the BJT pair is also pretty useful and effective as a MOS pair. Okay. With that, I will move on to looking at some examples and problems. So I'm going backwards and I've stopped on this slide, which is slide 8. So if we go backwards to slide 8, we stop at our first numerical, which is example 8.1 from chapter 8. So this is an example. It is solved quite well. Most of the basic concepts that you must understand in this chapter are captured in example 8.1. So please spend as much time as required to understand the problem and the solution. So with that, I can move on, but I'll spend an extra minute to make sure that I can highlight some of the important factors. So we are given a basic MOSFET pair consisting of two NMOS devices in common mode voltage applied. So we only have VCM applied, not differential. Under such circumstances, and all these values of VDD, VSS, Kn prime, Vt, I, the biasing current is given, Rd, the resistors in the drain circuits are given, no channel length modulation, that makes it easy. Also assume that the current source requires a minimum voltage VCS. The VCS is what has to be applied across the current source for it to work properly. Otherwise you have no bias. So with this condition and all these other things, you have to answer 5 queries. First of all, for this I given and all this other stuff, what is the overdrive voltage and what is the gate to source voltage? Part A. That is with, don't worry about any input signal yet. Then part B, we have a VCM of 0, common mode, which is still right, no input at all almost. Again find this voltage Vs, which is the voltage at the common source. Then the two drive currents or currents in the drains. Also these two voltages VD1, VD2 for VCM 0, then go to VCM plus 1, go to VCM minus 0.2. What is the highest permitted value of VCM? What is the lowest permitted value of VCM? So a lot of factors all connected to the common mode working of this. And the thing that I guess I should highlight, and you'll see this as you read the problem, is that for all these VCMs, many things don't change because we know that the differential mode amplifier rejects common mode signals. So whether the common mode is 0 or 1 or 1.1 or whatever, most of these things, the IDs and the VDs don't change, and you notice that behavior comes out clearly as you solve the problem. If you're looking for all the formulas, the drain currents are just half. The overdrive voltage can be gotten from here. VD1, VD2, you can calculate using this. VGS is V overdrive plus VT. V at the source, Vs, is Vg minus VGS. This voltage across the biasing source, current source, is this. And then lastly, it asks for the maximum and the minimum of VCM, and it can be derived using these. Okay, so please go ahead and spend as much time as required, but make sure you understand all the steps in this example. Alright, I'm going to move on to the next example, which is an exercise. So we have the answer in the textbook, but not the whole procedure. So this is related to the same amplifier as the previous slide, 8.1. Here, The only change is that the input, we are told that the two drain resistances RD are doubled. If that's the case, then he's asking what happens to the input common mode range. So the common mode range is something we derived here in the previous example, which is the difference between VCM lowest and VCM highest, which is about minus 0.28 to 1.5, or there is a range close to about 2 volts, right? What happens if the drain resistance is double? Will that range increase or decrease is what we are being asked. And as you can see, the range has become half. It's gone from minus 0.28 to 1. Previously, I think it was minus 0.28 to 1.75 or 1.5. So the range is definitely fallen. But how to do that is in my PDF. It's called Class Problems Part A, and page 1 of the PDF, exercise 8.1. If RD is doubled to 5K, then VD1 equals VD2 equals VDD minus half RD, which becomes 0.5 volts. So VC max can be from this formula as 1 volt. Similarly, IDs are shown 0.2 milliamps, and VGS is 0.82 using the same formulas that we have already used here for VGS, right? So we see common mode minimum is minus 0.28. So the common mode range is minus 0.28 to 1 volt. Okay. So that was exercise 8.1. Let's move on to slide 8.2, slide 14, where we are again looking at another exercise, again dealing with the same pair, the differential pair of example 8.1. Here we are being asked to discover what input value of this VCM now this is not VCM anymore, so maybe, well, it is, yeah, I don't think I should show this figure anymore. So let me take that out. That was a mistake. So, because now we are not operating in common mode anymore. Now we are putting a differential voltage VID. So if a value of VID, find the value of VID that causes Q1 to conduct the entire current I, and Q2 goes to 0, the current in Q2, and the corresponding values of VD1 and VD2, which is the drain voltage across the two devices. Then the opposite, we need the value of ID that causes Q2 to conduct the entire current, and then the corresponding range of the differential output voltage V22 minus VT1. Okay, so we use these formulas to solve this problem, and let me show you the steps. Okay, so Q1 only to be operating, that means VID is root 2 VOV, which comes out to be 0.45 volts. Q2 only to be operating, that means minus 0.45. So they only differ in sign. So the corresponding VD1 is 1.55 minus this, which is 0.5 volts. The corresponding VD2 will be just VD2, because this VD2 is nothing but the applied VDD, because this device Q2 is off, right? So when Q2 is off, the whole VDD applies, comes out at the output. So that is in case of only Q1 conducting. I think I shouldn't have mentioned this, so forget this for the moment. This comes in part B. In part B, only Q2 is conducting, then VDN is 1.5 because it's not conducting, Q1 is not conducting, and VD2 drops to 0.5. The differential output range is D2 minus VD1, which is 1.5 to 0.5 or 1 volt, and 0.5 to minus 1.5, which is minus 1 volt, depending on these two A and B's. Okay. All right. I will move on to slide 15, problem 8.2. I think I mentioned about this already. This is a PNP pair, not an NPN pair. So let's see if there's anything different that we need to worry about. Of course, you know that as soon as we say, did I say PNP? No, this is PMOS pair, not PNP pair. So PMOS pair, the formulas for saturation, etc., are slightly written differently, but the logic should be the same, right? All right. So here we are told that there is a PMOS pair. We're given a certain VTP, which is always negative, and this Kp, which is Kp prime into W by L, is given. Neglect channel length modulation. So first of all, for Vg1 equals Vg2 equals 0, that means at the gate no voltage is being applied. Find the overdrive voltage and V source to gate, right? Source to gate for each of Q1 and Q2. Also find Vs, the point here, and the two drain voltages Vd1 and Vd2. If the current source requires a minimum voltage of 0.4, find the input common mode range. Now, I think the next problem, hold on, let me just check. Yeah, so the next problem also is about the PMOS. And here, it's not common mode anymore. So here what we are doing is Vg2 is grounded. Yeah, Vg2 is grounded. A differential input voltage is applied to Vg1, which is Vid. Then we are asked to find the range of Vid needed to steer the bias current from one side of the pair to the other. Okay, so these two problems, 8.2 and 8.4, are about the same PMOS pair, and hopefully as we study this, we become a little more comfortable with MOS in general, because I know NMOS problems we've solved many, or we will do also homework and all that, but PMOS not enough, so we'll do a few more, at least a couple. All right. So the formulas to use are these. The currents ID1 and ID2, now you use Kp prime in this formula. The important thing to remember is that the V source to gate, for NMOS we call it VGS, gate to source, but here it's source to gate, is VTP plus VOV. Similarly, VD1, VD2 equals this formula. from here minus VSS. Then VC minimum, VC maximum, I think we need to find. So those have this formulas. Lastly, what is saturation for PMOS? So I tried to bring these formulas from our previous chapters, chapter 5 I think, where first of all VSG is VT plus VOV. Saturation means either condition you can use, the drain to gate has to be less than VTP, or source to drain has to be greater than VOV, right? That's the way to define saturation for PMOS devices. Alright, with that background, let's look at problem 8.2. So VG1, VG2 is 0, common mode input voltage is 0. So ID1 equals ID2, which is half of the biasing current 0.5. So you get 0.25 milliamps in each of the two devices. Now this formula also is true for ID. So from here we can find overdrive voltage to be 0.35. Now we need the source to gate voltage as G. So using this formula, that's 1.15. Then VD1 and VD2, the voltage at the drains, are using this formula minus 1.5. For both Q1 and Q2, the source to drain is this. Source to drain, this formula or this voltage is this. And since source to drain is greater than V overdrive, which is 0.35, we can say Q1 and Q2 are in saturation. So this 0.5 milliamp drain bias current in the source is good enough to put both Q1 and Q2 with no input voltage on the gates, is good enough to put both of them in saturation. Now we need to find what is the highest CM max, and that happens when CS is minimum. That means this has to be 0.4. So when CS is minimum, your common mode maximum can be calculated, and that's 2.5 minus this minus VSG. And we know VSG is 2.6, VSG is 1.15. I think we found it here, VSG. So if you plug all that in, you get the maximum common mode voltage is 0.95. The lowest VC minimum is what is needed to keep Q1 and Q2 in saturation, right? That means V D to gain is less than VTP. That is the condition, right? Which I show you here. VDG has to be less than VTP. So this VCM max and VCM min calculation is the opposite of what we see for NMOS. So I'm going to go back just quickly to slide 7. So what you see for max and min here is reversed in the case of PMOS. So just remember that fact. The definition is still the same, but the calculation logic is slightly different. So to find the lowest value, CM min, that means what is the value that can keep Q1 and Q2 still in saturation, and that is derived as this minus VTP, which is minus 2.3 volts. So your range is minus 2.3 to 0.95. It's quite a large range. for this PMOS device. So the explanation of this saturation here and this saturation here, I've added an extra slide or page, it's page 3A, to explain the saturation business. So for example, VDG has to be less than VTP, right? Less than or equals. Or VSD, source to drain, has to be greater than V over voltage. This is the circuit. We have the source, we have the drain, we have the gate. VCM is applied. So VDG has to be less than or equal to 0.8 because VTP is given as 0.8. Now we know that VDJ is minus 1.5 minus VCM minimum. So minus 1.5 minus V1's VCM is less than or equal to 0.8. You only have to test for equal to because the less than will always be satisfied automatically. So if you put the equal to equality, then you can calculate VCM minimum as minus 2.3, which is what I've shown here. So here's just a little more explanation. The other, which I think is also used somewhere else, VSD has to be greater than VOV, condition 1. VSG is VTP plus VOV. If VD equals VG, that means VSD equals VSG, which is VOV plus VTP. And remember, this VSD is connected like this, will always be greater than VOV because VTP always has some definite value, right? So if this is, let's say, 5, and this is 4, and this is 1, this 5 will always be greater than this 4, right? Which is the other condition for saturation, which I think we use here, right? VSD greater than VOV. Okay. All right. So that was problem 8.2, and we found the range for the input common mode. Like I said, 8.4 is a continuation of the previous problem for the same pair. Now it's not common mode anymore. We ground one of the inputs and we apply VID, which we don't know what it is, but it's not required for the problem. All he wants is the range of VID needed to steer the bias current from one side of the pair to the other. At each end of this range, give the value of the voltage at the common source terminal. So common source terminal here, and the drain voltage. So that's problem 8.4. Okay. First we need to find VOV in and I don't know if we found VOV here also. Yeah, we do find VOV. So maybe we have the same VOV. Yeah, we found the 0.35. So there's no need to calculate it twice. But anyway, given this is 0.5, so we use this. I guess here we use half of 0.5, right? Yeah, we use half of 0.5. We come up with 0.35. And here we're using 0.5. And we're coming up with 0.354. Okay. So this change isn't really making a big difference. It's still 0.354, which is slightly different from 0.350. Anyway, the overdrive voltage is still 0.35. This is a very small current, right? So that's why the overdrive voltage doesn't seem to be very different. So based on this overdrive voltage, the limits are, this minus root 2 VOV and plus root 2 VOV. So we have this range of minus 0.5 to plus 0.5 to take the current either totally into Q2 or totally into Q1. Okay. So at VID equals minus 0.5, that is Q2 cuts off and all the current is in Q1, we get Vs equals VTP equals 0.8 and VSG1 is Vs minus Vd from this circuit, source to gate, right, this, which is 0.8 minus of minus 0.15, 0.5 is 1.3 at this VID. And the drain current at that time is 0.5, so all the 0.5 goes into one of them, which is not a surprise. And the voltage is minus 0.5 at this VD1 here. Now, which means VG1 equals, so that means VG1 equals VD1, right? Because we just found VD1 and VG1 is given as VID, right? VG1, the gate voltage, is nothing but VID of minus 5. So when VG1 equals VD1, that means saturation. And I think this is what I was explaining in the previous page, page 3a, as saturation condition. Whenever we have the gate voltage equals the drain voltage, like shown here, that means saturation for MOS devices. And that's the logic I explained to you. Okay? All right. So VG1 equals VD1 means saturation. Same thing with the other input voltage of plus 0.5. Here Q1 will cut off and Q2 is operating with an input voltage of plus 5 only applied here. So VSG1 equals VTP is 0.8 as previously shown. V source is 0.5 plus 0.8, 1.3. So VSG2, SG2, which is source to gate here, is this 1.3. ID1 is 0.5. Sorry, this should be ID2. Mistake, big mistake. This, we calculated ID1 previously. So here, this should be ID2. I don't know why it's gone. Okay. So that should be ID2. Okay. Forgive me. So ID2 comes out also to be 0.5, which means that the entire bias current is going through ID2, the device 2. Based on that, if you calculate VD2, which is this minus 2.5 minus the drop in this 4K resistor, you'll get VD2 equals 0.5. So similar to the condition we saw here, if the gate voltage here on 2 equals the drain voltage here, that means saturation. And you can look at this explanation on the previous page to understand again why that means it's saturation. Okay. So we have answered this question. What happens when you have VID at the gates of both G1 or G2? What is the range? Minus 0.5 to plus 0.5. And what are the currents in each case? Okay. All right. So I hope that was useful. Let's see how many more problems we have. So I've got one more problem, which is basically an exercise. Another problem 810. And I think I have one more BJT exercise. Okay. So 3 more. So let's try and finish those quickly. So exercise 8.3. Here we have a MOS pair. The bias current is given as 0.5. These other things are given. Find the required values of W by L and the resulting GM, the transconductance, if the MOSFETs are operated at VOV of 0.2, 0.3, 0.4. So you see the answers are in a little table, right? At a VOV of 0.2, at a VOV of 0.3, at a VOV of 0.4. So if you know both VOV and I, you can find W by L, right? Using this formula. For each of these VOVs, give the maximum input voltage, VID, for which this factor, VID by 2, is limited to 0.1. Now where did this VID by 2 thing come? That's because in one of the formulas for the current, this VID by 2 by VOV. So he's talking about these two formulas that tell us what the currents are in each of the devices as a function of that input voltage VID, the input differential voltage VID. So the exercise says, if I give you the value of I, the bias current, I also give you the overdrive voltages, and I'm asking you to find the W by L and the GM, but also for each of these VOVs, give the maximum value of VID such that this factor is limited to 0.1. Now remember, VID by 2 by VOV is some kind of small signal condition, right? So if that factor is limited to 0.1, then what is the maximum VID is allowed? So you see how the VID is in millivolts, right? So this is the maximum in the answers. You can see that you're allowed to go up to a peak-to-peak signal of about 126 millivolts, 190 millivolts, 253 millivolts as your VOV goes higher, 0.2, 0.3, 0.4. So basically this has to do with these graphs. As you grow higher with the overdrive voltage, you can increase the magnitude or the amplitude of the signal that you apply on the input. Okay. So the formulas to use to find VOV, well, to find W by L. Now the W by L is also decreasing, right? In one case it's 50, then it decreases to 12.5. That's an important thing. That means that you have to change the construction of your device. So find that, and the transconductance and the VIDs. So the formulas are here in my PDF, exercise 8.3. Let's see, exercise 8.3. I've only done the calculation for one value of VOV, 0.2. So for point 2, you get W by L is 50, GM is 2, and VID is 126 millivolts. I haven't done the other two, but the method is pretty much the same. Okay. So I hope that was helpful in understanding the whole linearity business and what can be the maximum amplitude of the VID. And we have problem 810 from the back. Here is a design problem, right? Design the MOS differential amplifier to operate at VOV of 0.25 and to provide a transconductance of GM of 1. The technology available provides VT and this mu and COX as given. So basically we need to find two things, the W by L ratios and the bias current I. So how would you do this? This is problem 810 on page 4.5, sorry, page 5 of my PDF. GM has a pretty straightforward formula to find GM, and GM has to be 1 milliamps per volt. That gives us a I of 0.25. Another formula we use is I by 2, which is half the current in each of the two devices, is this, from which we can, and we are given VOV, right? VOV has to be 0.25. So based on that, you can come up with W by L to be 10. Okay, so that's a simple design problem from the back of the chapter. All right, we come to the very last example, which is the BJT. Now I said I'm not going to do too much in the way of BJT. So there's only one. Let's quickly look at it. So we are given a BJT circuit with PNP devices. The circuit is shown. We need to find V at this emitter, and then VC1 and VC2, which are these two voltages. Now a conducting transistor has a drop across the base emitter junction of 0.7 volts, and we can assume alpha is approximately 1. So this is the case of a BJT with a differential input signal applied. The differential input signal is 0.5 volts on one transistor base. The other transistor base is grounded. So this is not common mode. This is a differential input situation. So find VE, VC1, VC2. So to be able to solve this, we need to understand cutoff and saturation. With a situation like this, we know that one of them will be cut off, right? And the other will be conducting the full current. Now, cutoff means VEB less than 0.5, right? Now this is already 0.5. So as you increase the voltage here, until you get to, let's say, 1 volt here, this Q1 will be cut off, right? Because E to B will be less than 0.5. But once you go to, let's say, 0.7 here, this is already conducting. Because this is grounded, VEB will be greater than 0.5 and it will start to conduct. So the point is, the way this arrangement works, one of the devices will be automatically pushed into conducting or in the active stage, and the other automatically becomes cut off because its emitter base junction for the same applied voltage will push it into a reverse bias. Okay. So what I mean is, here's the solution to exercise 8.9. This is just everything that we see here. But I've written the fact that Q1 will go off because it will be reverse bias. Q2, even though its base is grounded. Now remember, these are PNPs, right? If it is NPN, the logic would be reversed. But with PNP and the base grounded, that particular transistor will come on. Q2 will come on because it meets this condition. Once you know that Q2 is on, you can do the rest of the analysis pretty quickly. As soon as this transistor is on, that we know that this VE will be 0.7 volts from here to ground. Then I in this circuit will be 5 minus 0.7, which is the voltage here, divided by the resistor 1K, which is 4.3 milliamps. Now we know that the collector current here will be 0 because this Q1 is off. There's nothing flowing down. And so all this applied voltage here will come to this point, VC1, because this current is 0 in this collector terminal of Q1. Q2 is conducting, so its collector current will be alpha times its emitter current. And alpha is luckily given to be 1, so the same 4.3 also appears in the collector. And the VC2 here will be the same minus 1.5 minus the drop here, right? So if the drop is 4.3 times 1, then you get the minus 0.7 as the voltage here. So that is VC2. Okay. All right. Sorry, I went over. I wasn't looking at the time, but that ends this recording.